Delete every atom in this room and light still bends. Because space itself has structure, it tells light where to go. The immediate takeaway is simple: space is not nothing. Strip matter away and geometry remains like hidden scaffolding. Gravity, waves, and quantum flickers still play on that stage. You can picture a riverbed after drought, still carving paths. Water is gone, yet channels remember where water flowed. Space works like that, but for light, time, and energy. I want to show how emptiness keeps surprising us. We will watch curvature steer beams and waves cross the void. We will see the vacuum push metal plates together. We will meet horizons that grow while galaxies fade from view. By the end, empty space will not feel empty at all. There is a starry gulf stretching between clusters, quiet and dark. In that gulf, gravity still has rules, even without atoms. In relativity, a vacuum is spacetime with no matter or radiation. You should care because this defines gravity as geometry itself. Curvature shapes paths, so objects fall along the straightest possible lines. Those lines are geodesics, drawn by the shape of spacetime. Remove the mass locally and shape can still persist. Nearby masses and waves from afar set boundary conditions. The shape then tells light and planets which way to move. That is the job of geometry, not an invisible force. Example: in real terms, light skims the sun and bends. The deflection is about 1.75 arcseconds near the solar limb. Starlight shifts that tiny amount, matching curved spacetime predictions. During eclipses, photographs caught stars displaced around the sun. Space, seemingly empty, carried the rulebook for those paths. Another case lives near black holes where empty regions swirl. Nothing touches you, yet your path still tightens inward. Curvature does the tugging, even if no air or dust. Bottom line, remove stuff and the map still moves you. Picture two long tunnels in a desert, crossing with laser beams. Those beams wait for ripples from nowhere, faint and brief. Gravitational waves are spacetime ripples that travel at light speed. You should care because they carry events across cosmic emptiness. Waves stretch and squeeze distances, so lengths subtly change in rhythm. Mirrors inch closer or farther by absurdly tiny amounts. The detectors use interference, comparing the phases of two beams. A passing wave slides the phases and the pattern flickers. The change is about 1 part in 10 to the 21. On 4-kilometer arms, that is smaller than a proton. Yet the signal peaks out because noise is tamed with care. Black holes merge far away, but their waves cross the vacuum. No medium is needed because geometry itself does the waving. We saw this first in 2015 and often since. Each chirp sketches mass, spin, and distance on a graph. Short version, ripples move freely where matter is absent. In that emptiness, the universe sends us time-stamped postcards. Now shrink to 2 metal plates, polished and almost touching. Between them, darkness seems absolute, but something still hums quietly. The quantum vacuum is not empty, but full of fluctuations. That matters because those flickers create forces you can measure. Modes of the electromagnetic field bounce between the plates. Only certain wavelengths fit the gap, like notes in a flute. Outside, more modes exist, so outside pressure is slightly higher. The plates feel a push together from that tiny imbalance. This effect is called the Casimir force, and it is real. At 200 nanometers, the pressure is noticeable in labs. Gold plates creep inward by a few piconewtons each square millimeter. Researchers cancel static charges, then watch the drift with care. Example: in numbers, the force scales strongly with separation distance. Have the gap, and the pressure leaps by a factor. Engineers consider this when designing micro machines with moving parts. Invisible vacuum forces can stall delicate gears and beams. So the picture is, removing matter uncovers pressure from fluctuations. Shift to a map of the cosmic web, filaments crossing emptiness. Vast voids look hollow, yet their shape still guides light. A void is an underdense region with far fewer galaxies inside. You care because voids reveal the background rules of expansion. They expand faster than average, so paths diverge gently inside. Light traveling through a void is slightly demagnified by curvature. That effect is small but measurable across many background galaxies. Astronomers stack lensing signals and the trend appears clearly. Rule of thumb: emptier regions nudge beams to spread apart. Filaments do the opposite, pulling paths into brighter arcs. A catalog might include thousands of voids above 100 megaparsecs. The stacked signal reaches a few percent in lensing strength. That is enough to test models of dark energy. We check whether growth and expansion agree across those scales. Example: in practice, surveys map shapes using billions of faint galaxies. The result is a stress test for gravity on large scales. Net result, even hollow space behaves like a quiet optical device. Fly through a bubble blown by dying stars, litter drifting at the edge. Inside the bubble, gas is thin, yet patterns still persist. A superbubble is a cavity carved by winds and many supernovae. You care because thin gas still carries fields and fast particles. Shock waves imprint structure, while turbulence stirs the remaining plasma. Magnetic fields thread the volume, guiding charged particles in arcs. Remove most atoms, and the fields become easier to see. Radio maps reveal synchrotron glow from spiraling electrons. Densities can drop below 1,000th of a particle per cubic centimeter. Magnetic strength sits around microgauss, steady across many light years. Cosmic rays ricochet, and pressure balances the surrounding medium. Example with numbers, shells race outward at thousands of kilometers per second. They sweep leftover dust into rims and leave hollows inside. Those hollows are not featureless, but alive with resonance. Observatories stitch together X-ray, radio, and optical mosaics. Together they show structure persisting where matter seems scarce. Bottom line, even debris fields display order within near emptiness. Drop down to a single ion glowing violet in a trap. Around it, the chamber is pumped until few atoms remain. Fields still exist there, even where particles rarely wander. A vacuum here means almost no particles, not zero fields. You care because fields can shape outcomes without direct pushes. Potentials change phases, so interference patterns shift without a force. The Aharonov-Bohm effect proves that strange but precise claim. Electrons travel two paths, both shielded from electric and magnetic fields. A loop encloses a magnetic potential, hidden behind metal walls. The interference fringes still slide because the potential shifts phase. In micron-scale rings, the shift is measured in lab devices. Fractions of a fringe show clear, reproducible phase changes. Rule of thumb, removing force does not remove influence. What counts is the information written into the potential. Another example lives in cavities with a single microwave photon. Atoms pass through and swap energy with near-empty fields. Spectra split into doublets, even with almost nothing inside. So the memory is, emptiness still carries instructions in potentials. Pan back to deep space, where galaxies thin against black. As matter dilutes, expansion is steered by something smoother. Dark energy is a uniform energy density that fills space. You should care because this sets the fate of the universe. A smooth energy density keeps pushing, so distant space expands faster. Regions with less matter empty into that steady background driver. The Hubble radius today is about 14 billion light-years. Beyond that distance, recession speeds outrun light due to expansion. No object breaks relativity, because space stretches between unbound points. Over time, more galaxies will drift beyond our view forever. Example with scale, the observable set could dwindle to our local group. Traces like the microwave background will fade below noise floors. A future observer might infer a quiet, static island universe. Yet the vacuum still contains curvature, horizons, and quantum activity. Net result, removing matter reveals expansion's engine more starkly. We started by deleting atoms, yet light still chose a path. Space proved it had rules baked into geometry and fields. Casimir pushes, wave chirps, and lensing all spoke from near nothing. If that flipped a switch for you, keep playing with ideas. I post deep dives like this at a friendly pace. One click saves it and brings the next curiosity your way. Before you go, picture that room with atoms erased again. Beams bend, plates creep, and a distant merger rings through. That is what space reveals when matter is removed.